Today's webinar was made possible through Forestry and Natural Resource Webinars, a partnership between North Carolina State University Cooperative Extension, Southern Regional Extension Forestry, and the Texas A&M Forest Service. I'd like to introduce today's speaker, Jeremy Stovall. Jeremy received his bachelor's in Environmental and Natural Resources from Clemson University, a master's in Natural Resources Forestry from the University of Vermont, and a PhD in Forestry and Forest Products from the Virginia Polytechnic Institute and State University. He is currently an assistant professor of silviculture at Stephen F. Austin State University. Jeremy?
All right, thank you for the introduction, Sean. Throughout today, if you have a question, please go ahead and type it in the chat box there, and we'll stop and address any questions you guys might have as we go through this. And Sean, if you wouldn't mind, go ahead and interrupt me if there's a question I may not spot it as I'm going through here. We'll start off with a question. There's 5 of these pop quizzes throughout the presentation, mostly so I can see what folks think, but these also might be important to pay attention to if you're trying to get CU credits here for the webinar. So take a moment here and figure out this first one here. So what's the primary goal of forest fertilizer application? Is it A, to increase financial returns, B, to increase diameter growth rates, C, to shift product distribution from pulpwood to sawtimber, or D, to shorten rotation length? I'll give you a moment here to answer. All right, so Sean's put the answers up right here on the screen, and it looks like the majority are voting for A here, with some other votes for B and D. Really, there's no wrong answer here. Fertilizer application, when done correctly, should do all of these things. What I would argue is that choices B, C, and D are sort of means to an end, and your ultimate end is A, to increase financial returns. So if we think here as an introduction about fertilizer application, what's the goal? Really, you're going to try and increase growth. You're going to try and focus that growth on your crop trees, and you're going to do that so you can improve product class and shorten your rotation. Fertilizer application really is a financial investment, and we need to think about it that way. So what I have here is average Southwide stumpage prices. This is 2010 data. It hasn't changed too much since then, unfortunately. But what you see is pulpwoods at $8, $10 per ton for pine, chip and saw close to 15, and saw timber at about 25 here. And so when we look at those values, if you can move 1 ton of your plantation from chip and saw at $15 a ton to saw timber at $25 a ton, that's going to give you a disproportionate value. And so that's really the goal of fertilizer application. It's to put a few extra inches of diameter growth onto your crop trees so you get that higher economic return at your next thinning operation, or ultimately primarily at your final harvest. So with fertilizer application, we really have to think about it as an investment. And with that, you all, I'm sure, know all investments are going to be subject to risk, and there's a few key risks we can think about when we think about forest fertilization. The first is that you can, say put 100 pounds of nitrogen on the ground, and your stand's going to grow more. Your stand's always going to grow, but it may not grow more than a stand right next to it where you didn't put that fertilizer out. So your stand may not respond to whatever fertilizer you apply. That's probably one of the larger risks with forest fertilizer application. Another risk is that your stand may respond. You may get a positive growth response, but by the end of the rotation, you may still have lost money or just not made enough money on that fertilizer application to justify the expense. So unlike a commercial thinning operation where you're going to make a little money when you remove, say 1 truckload of logs per acre, and that can offset the cost of that operation, fertilization is often called a timber stand improvement. Which means it really truly is an investment. You're going to pay to put fertilizer on the ground in a certain year, and you're not going to reap the economic returns from that for 5 years, maybe longer, depending on what type of fertilizer application. The other potential that we can see is that you do everything right, you get a great growth response to your fertilizer application, but then like you see in this photo here, I took this a couple weeks ago on some Weyerhaeuser land up in southeastern Oklahoma. but they had fertilized this stand once or twice already, and unfortunately got hit by some bad ice storms this winter. And as a result, you can see what were crop trees there are no longer going to be crop trees. And so that's a risk we find with really anything in forestry, regardless, because we're dealing with a longer rotation. So it's important to understand these risks and how these risks play out in your particular scenario. And this is one area with forest fertilization where industry has some pretty significant advantages over consulting foresters and over non-industrial private forest landowners. They often have economists on staff to assess these risks, whereas a consulting forester may have only themselves that they're working with, and so they sort of have to wear all the hats. And they also have access to a lot of data that most non-industrial private forest landowners and consulting foresters simply don't have access to, that give them a better idea of whether the stand may or may not respond to fertilizer application. And we'll give you an idea of some of those tools in the talk today. So keep in mind, when we're talking about fertilizer application, you always got to think of it in the context that it is an investment. Here's a broad outline for the talk. We're going to go over 4 main topics today around the general subject of fertilizer prescriptions. First, we're going to address the question, is your stand nutrient limited? This is something you have to understand before you even start thinking about fertilizing your stand. Once we understand whether a stand is nutrient limited or not, we need to know when you should fertilize, how much you should fertilize, and how you go about applying that fertilizer. And that's what the remainder of the talk will be focused on. I should point out that this talk builds upon an earlier talk where we looked a lot at how nutrients cycle within a forest, and understanding how nutrients cycle in a forest is going to be absolutely critical to putting together appropriate and proper forest fertilizer prescriptions. So you can always go back and look at that if you want to see more of that content about how particularly nitrogen and phosphorus cycle in forest ecosystems. Okay, so that brings us to our next pop quiz as we address this first question. Who is applying the most fertilizer to forests? And you've got 4 choices here. A is industry foresters in the Pacific Northwest. And by industry, I'm using that term very broadly to incorporate TMOs, REITs, and some of these new corporate structures we have. Industry in South America. C is industry in the U.S. South. And D is private forest landowners on a global scale throughout the world. So take a minute and let's see what you guys think. Okay, looks like we've got the answers up here, and we've got most folks going with industry in the, having some trouble with the pointer here, but most folks going with industry in the U.S. South, with some folks going for industry in South America. In fact, what we see today and over the last several decades is that the U.S. South leads the world in forest fertilizer application. In fact, more fertilizer is applied in the U.S. South as a region than in the rest of the forests in the world as of now. So if we look at some of the data, let me flip to the next slide. This is from Tim Alba, Lee Allen, and Tom Fox's 2007 paper, which did a great job addressing the state of forest fertilizer application in the U.S. South. But from 1969 to 2004, we fertilized 16 million acres of forests in the southern United States. Keep in mind, at the time, there was somewhere in the vicinity of 25 to 32 million acres of loblolly and slash pine plantations. By the mid-2000s, it was about 32 million acres. Now I think we're at about 34, 35 million acres. So basically, we fertilized half our pine plantations in the U.S. South. 91% of those were in loblolly pine rather than slash pine plantations, and what we found with a lot of research is that slash pine responds to fertilizer application, but not as much as loblolly does. Loblolly pine is more of a nutrient hog, so to speak, and is more responsive to fertilizer application. 80% of those were on the coastal plain, as opposed to the Piedmont, or if you're in the Western Gulf, the mountains up in Arkansas or Oklahoma. And part of that is, that's where a lot of the acreage is, and so that's why that's where a lot of the applications are. The other part of that is we find a lot of phosphorus deficient sands there on old Pleistocene terraces. We find a lot of potassium deficient stands, and across the board almost all our stands of certain ages are nitrogen deficient. And again, this is the vast majority of forced fertilization occurring in the world. It's not that other regions like South America couldn't respond to forced fertilizer application. We have some advantages they don't have. We have a fantastic road network, road infrastructure, and so we can get that fertilizer out there. And so part of it is the infrastructure that we have as well. This is redundant to that last webinar, but if there are some folks there who didn't see that last webinar, it's a good time to review. When we're asking if our stand is nutrient limited, we always have to keep in mind this changes over the duration of a rotation. And so what we have here is a figure looking at nitrogen, and what we tend to find is that there's a pulse of nitrogen early in a rotation. And that pulse of nitrogen is primarily due to slash from the previous clear-cut decomposing. This graphic is on the assumption that your previous land use was a forest of some type. And so that slash decomposes, releases nitrogen. At the same time, our newly planted trees you see along this blue line, they don't need much nitrogen. It's because we've only planted 500 or 600 of them per acre. They're small, they have closed crowns, and so they just don't need all the nitrogen that's out there. Somewhere on average around age 5 here, you see now the trees get larger, they close their canopy, the slash is decomposed, and so now we have this stand potential demand right here, this blue line I'm showing you. That's how much your stand could grow. Okay, so you've got this great potential for growth, but your trees aren't realizing it. Okay, they're not realizing if they could do it genetically, they just don't have the nutrients they need, in this example, nitrogen. And so this is where we have that opportunity for fertilizer application. By adding nitrogen fertilizer, we could go from here to up here and get that growth response that we're looking for. But keep in mind, early in a rotation, nitrogen does not tend to be limiting. That's not the same story for some other nutrients, and we'll get to that a little bit later. So we've got a sense of when nutrients may be more limiting in a plantation, but we still need to understand for our specific stand that we're considering fertilizing, is it nutrient limited or not, and most importantly, what nutrients are limiting it. It doesn't do you any good to apply nitrogen fertilizer to a stand that's primarily limited by phosphorus. You can apply insanely high rates of nitrogen fertilizer and get no growth response, when just a small amount of phosphorus could have doubled your growth in extreme cases. And so we really have to figure out what nutrients are limiting. I've got here 2 categories, sort of what tools does industry use, and again I'm using industry very broadly, including TMOs and REITs. And then what tools can forestry consultants or non-industrial private forest landowners that aren't buying into the Forest Productivity Cooperative or any of these other industry university research cooperatives, what tools can they use to try and assess whether their stands are limited or not? And so if we look at all these tools, one of the important ones that industry is using right now is leaf area index, which is just a rough idea of how many square feet of leaves do you have per each square foot of ground, and with the general idea that nutrients are growing leaves, the leaves are growing the trees, and that's where you get your return off that wood. And so what they figured out is they can actually use some Landsat data, publicly available data, and they can figure out that, for example, this stand right here has a leaf area index of 1.3 to 2.3. That's low. That's a stand that is likely to respond to fertilizer application, because if you put the right nutrients out there, they'll put on more leaf area and you'll get more growth. Whereas these darker maroon stands like this one right here, for example, they already have a leaf area index over 3.3. They're probably not as nutrient limited. So if you apply fertilizer to those stands, sure, you might get a growth response, but it's probably small enough that it may not be economically viable. So you can see very quickly from some geospatial data now, industry can look at their whole portfolio of stands and use some pretty simple data to make decisions. If their tree farm is 500,000 acres and they know they can only fertilize 15,000 acres this year, this allows them to prioritize the stands. They still need some more information though, because they don't know if this stand right here that's got a leaf area index of 1.3, they don't necessarily know just from this. Is it nitrogen limited, phosphorus limited, potassium limited, or perhaps by some micronutrients such as boron? So they also do a lot of soils work with this. And obviously the vast majority of that is proprietary. Here you have just a very brief example of what some of these industry foresters have access to. This is an example from the Campbell Group. But if you go out with a Campbell Group forester, before they go out into the field, if they're going to make a prescription at establishment for some sort of fertilizer application, they'll go into their mapping system and they'll print out their stand maps. And with those stand maps come all this sophisticated soil and geological mapping that they've previously done. And so instead of knowing that it's a Cecil soil series, for example, or a Tonkawa soil series, they have this alphanumeric code that, each of those numbers and letters has some meaning. Many of the field foresters, don't focus on the meanings of those too much because they also get this sort of information over here. This stand would respond well to 125 pounds per acre of diammonium phosphate or DAP with vegetation control, and they know that on their compartment, they may be looking at 12.1 acres of that soil type. And then, of course, they get this map, and they can see all that put out on the map, so they know spatially where everything is. You can see they'll get a map for mid-rotation fertilizer response 2. Does it have a high potential for response or medium potential for response? So that's a great tool. Obviously, an enormous amount of work and research went into developing it, but it's a tool that many of these TMOs and REITs have access to that the consulting forester, the non-industrial private forest landowner, they do not. And so if we look, there are some tools they do have access to. They're not going to be quite that convenient. One of the better ones out there probably is simply getting foliage from a stand in question, taking it to your local soil, plant, and water analysis lab at a local university, sending that in, and analyzing those the nutrients in those needles. And so what you can see for loblolly pine, if nitrogen content is less than 1.2%, phosphorus content is less than 0.12%, potassium content is less than 0.3% during the growing season, those are likely stands that are limited by that nutrient. And so you can get this analysis. It's relatively cheap. And from that information, you can say, yeah, this stand's likely to respond. No, this stand is unlikely to respond, and you can make management decisions. The challenge around this is, one, you have to physically sample each stand, and if you're dealing with larger landownerships and a lot of stands, you can imagine that gets costly, not necessarily from the soil testing standpoint, but just from getting someone in the field to do all this sampling. Physically getting to the stands can be very cost intensive. The other downside is there's a lot of noise around this. For example, when I was doing my PhD work at Virginia Tech, we had a small research trial in southwestern Virginia with loblolly pine. And what we did some of these analyses, and we found that the foliar nitrogen content in that stand was 1.6%. You look at that and you think, well, this site isn't nitrogen limited, it's unlikely to respond. We put the trial in anyway, fertilized it, had a fertilized treatment, a control treatment, and lo and behold, we got something like a 20-25% volume growth response in the first 6 years from fertilizer application. So this doesn't always work perfectly. There's a lot of noise around these numbers. But again, if you don't have access to leaf area index or some of these other more sophisticated soil mapping databases, this is sort of the best we can do. The other thing you can look at is soil tests, and again, work with your local soil testing lab. And we have some rough numbers for some nutrients. If you're in a state that's using a Malick 3 soils test, and you get a phosphorus number less than 6 parts per million, potassium less than 12 parts per million, calcium less than 40 parts per million, or magnesium less than 10 parts per million, that's very indicative that those soils are limited by those nutrients. The challenge here is we're working in forestry. We're dealing with a perennial crop, and a perennial crop that roots basically as deep as it can. And so typically when you do soil tests, and all these soil testing labs, they're really set up a lot more for agriculture, where you're dealing with an annual crop that's generally shallow rooted, and so all the sampling tends to occur in the top 6 inches, 4 inches of the soil. With forestry, you got to keep in mind it may be important when you're sampling soil to get soil at greater depth in order to get a sense, especially if you're working with spotosols, of, maybe you don't have nutrients in that A horizon, but right below it you have that spodic horizon with the rich, dark soil where all the organic matter is accumulated. Maybe that's where all the roots are, and maybe that's where all the phosphorus is. So you just got to keep that in mind. With forestry, you're dealing with a deep-rooted crop. Make sure your sampling is appropriate for that. That being said, the vast majority of fine roots where a lot of these nutrients are absorbed are in the upper few inches of the soil surface. So it's not a huge problem, but just something you need to consider. The challenge here is nitrogen is the nutrient that is most limiting in our forests, and unfortunately, nitrogen is much more difficult to predict from soil testing. We do a very good job. We're very efficient at telling you how much nitrogen is out there in that soil. That's total nitrogen. The vast majority of that isn't currently available to the plant. It has to be mineralized first. There are tests out there that test either the aerobic or anaerobic mineralization of nitrogen, and those tests do correlate much better to fertilizer growth response than total nitrogen numbers do. The challenge is, depending on the test, it may take 7 days, it may take 7 weeks, and they're more expensive. And so I would say this is a major barrier to non-industrial private forest landowners applying fertilizer. They don't necessarily have as good a sense as industry does of what nutrients are going to be limiting on their stands. And even if they do, even if you do get good data here from foliar and soil testing, and you have a good sense of what nutrient is limiting on your stand, you don't have as good a sense of what magnitude that volume growth response will be from fertilizer application. And so anytime we have less knowledge, of course, that's going to increase our risk from an economic standpoint. And so really, I've talked with the Texas A&M Forest Service foresters who work with landowners here in Texas, and none of them had an example where a consultant was recommending forest fertilization, or where they had a non-industrial private forest landowner who was doing fertilization. And I think this is why. It's just going to be a risky investment for them. They probably have stands out there that would respond great and yield them a great economic return. They just don't necessarily know what those stands are or what to do on them. And so hopefully in the coming years we can get some of these tools that industry is using and produce analogs of them that are better available to those constituencies. But we're not there yet. One of the best models that's out there for those constituencies are some simplified soil models. And the best example of one of those is the CRIFF Forest Soil Classification Scheme. CRIFF is an acronym standing for Cooperative Research in Forest Fertilization, and this has been a product of the University of Florida. A number of researchers there, most currently Eric Jokula, are working with this system. And what this system basically does, as a forester, you don't really care if you have a Tonkawa series soil or a Rain series soil. What you care about is how that soil is going to alter how you need to manage that forest, what it means for your silvicultural actions. And so what they've done is they've basically put together these groups you see here, A through H, and they have fertilizer recommendations for each of these groups. And they have them split up based on basically the soil textural properties more than anything, and the organic matter where that's located. But if you look at these, they vary on the drainage class from very poorly drained to excessively well drained. They vary in whether they have a spodtic horizon or not. And you can see, of course, South Georgia, North Florida, they have a lot of spodosols. We don't have as many in other places in the South, but that's where the system was developed. And they vary in their texture, depending on how sandy they are, depending on if it's more of a humic soil, has an organic layer on top, or if it's just a very, very deep sand before you get down to the clay layer. So in this example, a BT horizon or an argillic horizon. So instead of having the thousands of soil series that we have in the South, if we could group everything into A through H, and we generally know how each of those letters responds to forest fertilizer application, we're in much better shape. You can see the citation there below, but if you just Google search CRIFF Forest Soils Classification, they have a number of good extension publications I would encourage you to go look at that may help you figure out where your soils are. If you're located in South Georgia, North Florida, they even have some of these publications that list individual soil series and which letter they best align with, so you don't even have to do that work. Looking at an example, here's what these different soils look like. And so you can see they have some very different properties. Obviously, some big differences in the drainage class where you can see A, there's a lot of glaying there, gray matter, which indicates a poorly drained soil, versus G, where you can see all the iron in this horizon is nice and yellow-red, so it's well oxidized. That's a well-drained soil. You can see some of those obvious differences like that. And what they've done is basically just, put together recommendations on how you fertilize these stands. So for CRIFF A series, which are those poorly drained clayier soils that tend to occur on a band in the lower coastal plain, designated by this red line right here, what we found is those tend to be extremely phosphorus deficient soils. Those are soils you definitely want to apply phosphorus on at establishment, and they found on some of the most severely deficient ones, it can take a stand that basically is never going to be anything more than a pretty terrible pulpwood stand and convert it into a pretty fantastic saw timber stand. And so knowing this, I mean, it can make a huge impact on whether a site, can even be managed in a plantation or whether it's a pretty high-performing plantation. And again, we went over this during the last webinar, but phosphorus, with how it cycles in the soil and how tightly it bonds to clay, off an application of 25 to 50 pounds of phosphorus at the beginning of one rotation, they're actually seeing a growth response into the second rotation. So being aware of this can make a huge difference in how your forest grows and what your economic returns are, what your rotation lengths are. Okay, so there's a look at how we determine nutrient limitations in forest, but the take-home message is, the U.S. South leads the world in forest fertilizer application because we have a lot of stands that respond well and give us a good economic return. The vast majority of our forests in the southern U.S. are limited primarily by nitrogen and phosphorus, but we do have stands limited by potassium on some of our Pleistocene terraces on the lower coastal plain. We do have stands limited by boron or other micronutrients like copper. And those can respond very well from a nutrient addition. It's a critical step if you're going to fertilize a stand to understand what nutrients are limiting your forest, because if you put nutrients out there and that's not what's limiting to that stand, you're basically pouring money on the ground and getting no response for it. And we've looked at some of those tools that you can use to determine if a particular nutrient is limiting to your particular stand. Okay. Now that we have a sense of whether our stands are nutrient limited or not and what tools are available, let's talk about when you should fertilize. And that leads us into our third pop quiz here. And so this one is, when should you apply nitrogen? I'm focusing on nitrogen here. Fertilizer in a rotation. We've already looked at that a little, so you've got a hint here. But choice A is during site preparation. Choice B is 2 years before a thinning operation. Choice C is right after a thinning operation, and choice D is 1 year before clear cutting and ending your rotation. So what do folks think? Okay, so it looks like the vast majority of folks here are voting for C, with one choice for A and one choice for B. So let's go look at a little data that can help us tease out the answer to this one a little bit more. So the broad question, when you should apply fertilizer, we can really split that into 3 key components. First, when are nutrients limiting? If nutrients aren't limiting at that point in the rotation, we don't need to be applying fertilizer. Second is, how long does a stand take to respond? And once it has responded, what's the duration of that response? And so if you look, I've got a photo to the right. You can see a recently machine-planted loblolly pine plantation. So maybe a little hard to see here. There's a seedling right there. You can see where the machine planter's gone down this row. Okay? This is a site that's been windrowed. You can see a windrow in the background on that photo, so there's almost no slash. But this is an example of a site prep fertilizer application. If you look at this site, what we find, and what we've gone over already, is if you have any slash well distributed out on your stand, it doesn't make sense to apply nitrogen fertilizer at site prep. The trees aren't limited by it. If you are going to windrow, as they did here, it may make sense to apply nitrogen fertilizer. The cheaper option, of course, though, would be don't windrow. Anything you can do to leave your slash better distributed throughout the stand is going to really eliminate that need to apply a site prep nitrogen fertilizer application. Okay? The other thing we've got to look at is how long it takes a stand to respond to fertilizer, and it's not immediate. Okay? If you apply nitrogen fertilizer, you're not going to see your growth response immediately. If you apply phosphorus fertilizer, you're not going to see your growth response immediately. Let's look at some data for each of those. Okay? What we tend to find in terms of the limitation first, though, is that phosphorus, potassium, or some other micronutrients such as boron can be limiting at an establishment. If they're limiting on that site, they're unlikely to be in sufficient abundance in the slash that you get that pulse as it decomposes. If such a deficiency exists, site prep fertilizer application is absolutely recommended at establishment. Again, nitrogen, if slash is left reasonably well distributed, isn't typically limited until the stand gets closer to crown closure, and so we typically, see less establishment application or site prep application of nitrogen and more mid-rotation application of nitrogen fertilizers. And so if we look, here's some data from that same paper on historical patterns of forest fertilization in the southeastern U.S. And what we see here is, first off, there's very little fertilizer application until about 1990. Then it really takes off. And what we see is that the vast majority of applications are mid-rotation with fewer at establishment. This was in part because when they started applying fertilizer, obviously they had more stands in the middle of the rotation than they had acreage that was being established each year. But it's also because they realized that nitrogen's not as limiting an establishment. Other nutrients like phosphorus maybe. You see this declining here. The establishment fertilization is declining while the mid-rotation fertilizer application remains more constant. And so current recommendations would be, really not to focus on nitrogen application at establishment. It's going to be more limiting at mid-rotation. Those other nutrients may be limiting at establishment. Here's some data. You see the citation down here from a Southern Journal of Applied Forestry publication, including Lee Allen as a co-author. But what they looked at in this study were some of these lower coastal plain sites with poorly drained clay soils that they knew were phosphorus limited. And what we found here is a control treatment, a treatment that they bedded only, a treatment that they fertilized with phosphorus at establishment only, and a treatment that they both bedded and fertilized with phosphorus at establishment. And what they found is, you can see, they fertilized with phosphorus at establishment, and by age 10, the control treatment is about 12 feet tall. The fertilized treatment is, close to 20-something feet tall. By age 12, it's at about, 16 feet versus, 28-ish feet there. This would be an example. Imagine projecting that out to age 25. They basically doubled site index on this site just by applying phosphorus fertilizer at establishment. Okay? So with that scenario where you have these sites, obviously we're probably not going to get to our first commercial fin on these sites until, age 11, 12 or so. But if you've applied P at establishment, you're going to get a lot more value out of that commercial fin, and it's going to come earlier in the rotation. So that's the take-home message with phosphorus-limited sites in an establishment P fertilizer application. It's a different story with the mid-rotation nitrogen application. Here's some data from Ralph Amateus at Virginia Tech, and again Lee Allen, published in 2000. And they looked at mid-rotation nitrogen and phosphorus application. I don't have it listed here, but along with these treatments, we have a control where no fertilizer was applied. 100 pounds of nitrogen fertilizer applied at mid-rotation, 200 pounds, and 300 pounds of nitrogen fertilizer. And what I don't have shown here is, along with that nitrogen, they also applied 50 pounds of P with each of these treatments. So phosphorus limitations were taken care of where they exist. And what I have here is two graphs for you, one showing the height, okay, and this is not the age. This is the growing seasons after that mid-rotation fertilizer application. And what you see is, here's the control, here's 100 pounds of N, and then it's hard to discern the 200 and 300 pounds of N lines because they're right on top of each other. But you can see they continue to pull away for a period of time, okay? And so it takes more time for that nitrogen application response to occur. And so you can see it's a very small difference right here. So if you had applied nitrogen fertilizer mid-rotation and thinned a year later, you basically, fertilized some trees that never had a chance to respond to that fertilizer application but uptook those nutrients, and then you removed them a year later. So you wasted some of your money in that operation most likely. If we look, basal area over here in square feet per acre, this figure is going to be a little more telling. Everything else is the same on here. But what you see by 10 years after fertilizer application, between 8 and 10 years, you can see that basal area response is starting to level off. It's understandable why. Look at the basal areas we're at. We're between 145 and 155. You're starting to get a lot of density-dependent mortality in these stands. And you can see that most in the application where they applied 300 pounds of nitrogen fertilizer. That site clearly, even with that nitrogen, isn't able to carry more than about 160-something square feet of basal area per acre. But again, you see the same trend. It takes a few years for nitrogen fertilizer response to occur. If we're under the framework, I've got a red line on here. Say your target from a basal area standpoint for applying a thinning operation is about 135 square feet per acre. I know some people like a little more than that, some people like a little less than that, but if that's the case, you can see where each line crosses it, okay? So it's going to take you about 6-7 years if you didn't apply fertilizer from that point in the rotation before you're looking at that thinning operation. Well, if you apply 100 pounds of nitrogen per acre, you've shortened that up by about a year, a little bit more here. Now we're at about 5 years with a 200 pound per acre nitrogen application, and we're down to about 4 years after for a 300 pound per acre nitrogen application. And so here we're seeing it's going to take you probably, 4 or 5 years on average before you're even going to want to think about thinning that stand after a mid-rotation nitrogen application. And then that response duration, it tapers off at some point, largely due to stand dynamics. And so you don't want to go too long either. And so if we look at some of those general guidelines, we'll come back to that briefly, but if we look at some of those general guidelines, here they are. So for fertilizing with nitrogen and phosphorus at mid-rotation, a mid-rotation application, you really want to have it done at least 5 years before you thin or clear cut to give your trees a time to respond so you yield the economic return on that application. If you're going to apply multiple applications of fertilizer, which some companies, such as Weyerhaeuser, for example, are doing, you probably want to space those every 5 to 8 years because that response sort of tapers off. And the goal should really be to increase the final diameter of those crop trees. And so if you fertilize right after a thinning, you've just removed trees that aren't going to be your crop trees, and you're not essentially wasting those nutrients you apply with fertilizer on non-crop trees. Okay, so 5 to 8 years tends to be a good goal before a thinning operation or before another application, mid-rotation application of nitrogen fertilizer. Now we saw, if you're going to fertilize with peat establishment on these clay soils in the lower coastal plain, do that right away. That's going to shorten your time to first thin. That's going to shorten your whole rotation life. You don't have to worry about timing as much with that one because it's such a great response often. Okay, let's go back here and look at time within a year now. So you've decided to fertilize. When during the year do you fertilize? And what we found is basically that March to May is about the ideal time in most places to fertilize. It's going to vary depending on where you are, how far north and south, coastal plain or Piedmont, for example. But in general, what you're focused on is you really want to avoid hot weather. And you want to avoid hot weather more so with some fertilizers than others. Urea is a very common nitrogen fertilizer, but what happens if you apply urea during hot weather, it can volatilize. So you see this diagram over here with this balloon. Basically what that's saying is you put the urea on the ground, it actually undergoes a biological reaction mediated by an enzyme that converts that urea chemically into a gaseous form, and that gas is lost to the atmosphere. And if it's in the atmosphere, your trees can't get it, and so you may have applied 200 pounds per acre, but if 100 pounds per acre is volatilized, you've basically just applied 100 pounds per acre, and you've wasted half your fertilizer. Because that reaction is mediated by an enzyme, anytime it gets warmer, enzymes operate more quickly, and so we want to avoid hot weather with our urea fertilizer applications to avoid that. We're finding more and more how to avoid that too chemically, and so they found if you put a little boron out there, it will actually reduce volatilization. Weyerhaeuser is selling a specialty fertilizer now. I believe they call it arborite, and basically I believe it is a urea fertilizer coated in monoammonium phosphate, but I think they glue it all together with a boron glue, and part of why they're using that boron glue is to minimize volatilization in the nitrogen fertilizers they're applying. So that's one example of a product out there now that can, alter some of this volatilization that we're seeing. There's a lot of other products out there. I'm not trying to pitch any one or the other. And I've got down here efficacy to be determined. I know there's a PhD student at Virginia Tech right now, Jay Raymond, who's doing a lot of research on this. They've put out some stable isotopes, N15, to really track where nitrogen goes when it's applied as a fertilizer. And he should have a lot of pretty cool results here relatively soon on what works, what doesn't work, how much of your fertilizer may be volatilizing. So we're getting more and more information, and we'll have that into the future. So you want to avoid hot weather. You also want to apply during the growing season. You don't want to put this out there in the dead of winter when it's nice and cold, so you get no volatilization, but also when your pines are, not doing much, because then, on a sandy site, you've got a little potential for leaching that nitrogen out. The other, flip side of that coin is that nitrogen is going to go somewhere. And so it may go into non-crop vegetation that are more active at that particular temperature. And so you want to apply it when your pines are actively growing so they uptake as much of it as possible. Nitrogen is pretty mobile in the soil, and so you really want your trees transpiring because that's the primary way nitrogen is taken into a tree. It's through mass flow through soil water. And so you basically want your trees transpiring. And so again, March to May is the beginning of the growing season. Your trees are transpiring. It's not over maybe 80 degrees, but it's also not below maybe 50 degrees Fahrenheit ideally. And that's when you're going to get greater efficiency out of your fertilizer application. Okay, we've already looked at the review there. So this brings us on to our next topic, which is how much fertilizer to apply. So if your stand's nutrient limited, we've seen when in a rotation and when during the year to apply that fertilizer. Now let's think about how much fertilizer you want to put out there. And here's our next pop quiz. We've looked at a number of different rates for nitrogen here on some of these graphs, but let's have you all take a stab at what is a typical rate of nitrogen applied at mid-rotation. Is it A, 38 pounds per acre, B, 75 pounds per acre, C, 150 pounds per acre, or D, 300 pounds per acre? Okay, Sean's posted our results here, and it looks like we've got one for A, and pretty much everyone else who answered was C. And again, C does tend to be the most common rate out of all of these. And we'll look at some data right here on why that is. And so here again, we have a figure from that Tom Fox, Lee Allen paper. This is a different paper, actually, from 2007. But what they looked at in this one was some data from the Forest Productivity Co-op. And it's kind of a complicated figure, but we'll go through it. What they had is 3 different rates of nitrogen fertilizer application: 100 pounds per acre, 200 pounds per acre, and 300 pounds per acre. And at each of those rates of nitrogen fertilizer application, they also applied no phosphorus, 25 pounds of phosphorus, and 50 pounds of phosphorus per acre. These are all mid-rotation applications. So here's 200 pounds per acre of nitrogen with no phosphorus, 25 pounds phosphorus, 50 pounds phosphorus. And what you're seeing on the y-axis here is volume growth response in cubic feet of wood per acre. And so what they looked at with this data was, what rates should we apply? And what you'll notice, see how you have this nice steep linear line here from 0 to 100 pounds? So, we got a huge growth response there. From 100 pounds of nitrogen to 200 pounds nitrogen per acre, again, we doubled. We got a huge growth response there. From 200 to 300 pounds, it levels off. Okay, all these fertilizers have a cost, and so the recommendation there was, go with about 200 pounds per acre. 300 you're going to be spending more than you need to. 100 you're not getting enough growth response. And of course, this data came out before oil and gas prices really started spiking around 2005. Of course, most nitrogen fertilizers, making them is a very energy-intensive process, and so their costs are very, very closely linked to the price of a barrel of oil. And so when gas prices go up, fertilizer prices go up. And so since then, people have been trying to back off some on their rates because fertilizers have gotten a lot more expensive. And so a very typical rate today would be 150 pounds nitrogen per acre. It might even be less than that. Some people may be applying 100 pounds per acre just more frequently now due to the cost of fertilizer. And you can see that there are some benefits to 50 pounds of phosphorus per acre, but a very typical mid-rotation prescription might include 25, and here again you see on this data set why. There's not as much separation between the 25 and 50, certainly compared to the 0 and 25. Now when we look at a bag of fertilizer, it has a fertilizer rate on it. So let's talk a little bit about what fertilizers we might apply, what those rates on the mean, and how you go about putting together a prescription from that. And so you get 3 numbers on a bag of fertilizer. So this one example is 5, 10, 15. And what that stands for is the first number is nitrogen, the second number is phosphorus, and the third number is potassium. So it's the NPK rate. If only it were that easy, we barely would need this slide. It'd be nice and simple. But unfortunately, due to some historical reasons, the N number is convenient. It actually reflects elemental N. So if you've got a 100-pound bag of fertilizer with this prescription rate on it, you're applying 5 pounds of N if you dump that whole bag of fertilizer out. That's easy. Unfortunately, the P number is not elemental phosphorus. It's P2O5. And so if you think you're applying 10 pounds of phosphorus dumping that 100-pound bag out, you would be wrong. You're only actually applying 4.4 pounds of phosphorus, and it's because the rate is for P2O5, and about 56% of that is oxygen. And we really don't care about that oxygen because the tree doesn't get oxygen from the soil, it gets oxygen from the atmosphere, and it's got all it needs. They're not oxygen limited. And so what we end up seeing is that you have to take that number and multiply it by 44%, and it's simply because the atomic weight of P is 30.97, the atomic weight of oxygen is 16.00, so if you take 30.97 times 2, you know that the phosphorus in each molecule of P2O5 has an atomic weight of 61.94. If you add to that 61.94, 16 times 5, we know that total molecule weighs 141.94. Divide 61.94 by 141.94, and you get this 44%. And so really, every time you see the P number on a bag of fertilizer, you got to multiply it by 44%. Exact same story for potassium, except it's K2O instead of P2O5. The atomic weights are a little different, but the take-home message is it's 83%. So if you see a bag of fertilizer with 10 for a K rate, it's really 8.3 pounds, or 8.3 pounds in that 100-pound bag that's actually elemental potassium. So that's how the fertilizer rates work, just a reminder probably for most folks. Then let's look at some rates and different fertilizers that we see used in forestry. Urea is very commonly used. It has a rate of 4500. It's a nitrogen fertilizer, and we've already gone over volatilization. That can be an issue with urea. Ammonium nitrate used to be more commonly used than it is today. It has a rate of 3300. It's not longer sold as much. It's much more tightly regulated, and the primary reason for that is it was the main chemical used in the truck bomb that Timothy McVeigh detonated at Oklahoma City in 1995, I believe. So it can be used as an explosive, and it is much more difficult to get access to now as a result. A very common fertilizer in forestry is going to be diammonium phosphate, which we almost always just abbreviate as DAP. Its chemical analysis is 1846 years, so it's primarily a phosphorus fertilizer, but you can see it is 18% nitrogen by weight. And so it's very convenient, and then you may be applying it primarily as a phosphorus fertilizer, but you get basically some free nitrogen along with it. Another one that's very common for phosphorus is concentrated superphosphate. If you're familiar with triple superphosphate or TSP, it's the same thing. This chemical goes by a number of different names. It's 0,44,0, and it's a very common water-soluble phosphorus fertilizer. There's DAP on here again. Another one would be rock phosphate. It's 0,15,0. It's not water-soluble. It is soluble in acids. It tends to be a little cheaper than triple superphosphate here. Fertilizer prices are extremely volatile. They vary, month to month. They vary year to year. But often it may actually be cheaper to apply, you'd have to apply almost 3 times as much rock phosphate as concentrated superphosphate. But, if it's less than a third the cost, it may end up actually being more economically viable to apply this fertilizer sometimes. For phosphorus, we tend to get different types of potash. Some of them are called, for example, muriate of potash, and its rate is 0,060. When you're going to put an actual fertilizer prescription together, usually what you want to start with is knowing what elemental rate do I want to apply. And then from that, figure out what fertilizers you can get for the cheapest or your contractor can get for the cheapest, and then figure out from that how many pounds of those do they need to apply per acre. So I know this is a very complicated table, but it's very simple in concept. And so this is an example where the forester wants to apply 50 pounds of elemental K per acre, 25 pounds of elemental P per acre, and 200 pounds of elemental N per acre to their stand. And they've decided the cheapest fertilizers they can get to do this are urea, DAP, and potash. And so let's start with the potassium here because it's simple. It's all by itself. And so what we've done, the rate on the bag for potash is 0,060, but we know that that 60 is really for K2O. So we've got to multiply it by our 83.3%, and when we do that, 60 times 0.833 comes out as 0,050 as our elemental rate on that bag. And so each bag of potash fertilizer is 50% potassium by weight. We know we want 50 pounds of elemental K per acre, and so all you do is, here's the elemental rate again, you divide that 50 by 0.5. Because that's 50% K, express it as a ratio, and it becomes 0.5. And so divide 50 by 0.5, and you tell the contractor we want to apply 100 pounds of potash per acre. We do the same thing here for phosphorus with diammonium phosphate. We know that, it's 46% P2O5, and so we have to multiply that by this 43.6%, and so we know the elemental rate is 1820. And so from that, we do the same thing we just did with the potash. We know we want 25 pounds per acre, and we know that our bag is 20% K, and so we divide 25 by 0.2, and we know we're applying 125 pounds of DAP per acre. When you look at DAP low, you're also going to be applying some nitrogen. And so what we've got to do now is multiply our 125 pounds of DAP per acre we're applying times 0.18, because that bag's 18% nitrogen by weight. And so what we realize is we're also applying 22.5 pounds of nitrogen per acre with that diammonium phosphate. So what we do for nitrogen, nitrogen's easy to work with because you don't have to convert the ratio on the bag. We know we want 200 pounds per acre. We know we've already applied 22.5 pounds per acre, so 200 minus 22.5 is 177.5 pounds per acre. And so now all we do is take that 177.5, divide it by 45%, which becomes 0.45, and we know we're applying 395 pounds of urea per acre. And so now you know what to order depending on the acreage of your tract. You can scale these per acre rates up. You know what to tell the contractor to apply per acre. 395 pounds of urea, 125 pounds of DAP, and 100 pounds of potash. And so I know, kind of complicated looking at this table. You may have to work through that. It's been a while since you've messed with fertilizer rates or had soils. But once you work through a few of them, it's pretty straightforward. And once you've worked out these elemental ratios for fertilizer, those really don't change too much. So it gets easier as you work with it a little bit. So for the Objective-C review, again, this looks like I copied this over wrong. It's the same as the one before. But to review, basically what we know is typical rates are about 150 pounds nitrogen, about 25 pounds P maybe at mid-rotation. With an establishment P application, you're looking at about 25 to 50 pounds of P per acre at establishment, 25 probably being more typical now. And we looked at how to actually apply those in terms of what materials you're applying and how you would go about calculating how much of them you need. So sorry that copied wrong. Okay, and so we're on to our final objective here. I know we only have 10 minutes left, but this is a quick one, so shouldn't be a problem. How is this fertilizer actually applied? And so here's our last pop quiz of the day. So in the U.S. South, how is most fertilizer operationally applied? And again, this is primarily by TMOs and REITs right now, but is it applied by hand, by helicopter, by fixed-wing aircraft, or by skidder? So take a minute and go ahead and answer that. Okay, might have been a trickier one here. So we've got, looks like 3 people going with by helicopter. Fortunately, no one said by hand. No one is going for fixed-wing aircraft, and the majority are choosing by skidder here. If you look, the majority in the U.S. South is actually applied right now by fixed-wing aircraft for a number of reasons. One, drift is less of a concern with fertilizer than it is with herbicide because the potential downsides are, less severe. You're not going to be killing a lot of non-target vegetation. So drift is less of an issue. The other thing is you can often get a slightly heavier load on a fixed-wing aircraft. Herbicides tend to be applied as liquids, and so they can go back and forth to the tanker truck and load that helicopter pretty easily, whereas with fertilizer it's often a solid that's being applied, and so that reloading with a helicopter isn't often going to be as convenient in the field since you're dealing with a solid. So those are a number of reasons why they're focused on fixed-wing aircraft. They do apply by all those other methods, not really by hand, but by helicopter, and by skidder happens also from time to time. So here's an example of a typical sort of modified skidder here set up to apply fertilizer. You can see it's got a large hopper in the back, and then this is actually the applicator right here on the back. This photo, you can see there's been over damaged trees. This is up in southeast Oklahoma, and this is an operational fertilizer application by Weyerhaeuser that they were doing a few weeks ago. So there's one example. Here's another example. Now you see a tractor towing a hopper that's got built-in applicator equipment there. Here's another example of tractor-drawn equipment in a loblolly pine plantation. So there's some variety in the equipment, as you would imagine. Here's another tractor with a much smaller hopper applying fertilizer in a younger stand. Here you see an example of a fixed-wing aircraft applying fertilizer, and so that's going to be a pretty typical piece of equipment. They tend to work out of smaller local airports, and again, with a fixed-wing aircraft versus a helicopter, you do have a little more range to work with, so that's another advantage to fixed-wing aircraft. This is an example of an application from a helicopter. This is actually in the Pacific Northwest, not the southeastern United States, but it can be done from helicopter. There are a number of things we need to consider when we sort of determine the rate in the application method. One of those, are we applying over the canopy, and how much our fertilizer may get hung up in the canopy? Another is, do we have an abundant shrub layer? Here's a stand with dense yaupon in the understory in East Texas. If you've got that shrub layer, one, you can hang up fertilizer, but two, if you're thinking about a skidder application, you can imagine it may be difficult to move a skidder through this stand, and even if you can get a skidder through there, you can see basically that hopper on the back, it flings the fertilizer out to the side. And so you can imagine if you're moving your skidder through between these rows right here and knocking those yaupon shrubs down, well, you're not doing anything to these over here. Your fertilizer is going to hit into that and fall down, and you're going to get a pretty uneven application. The other considerations are track location, and that's going to be very similar to what we think about with aerial herbicide application. Are you near a chicken house or a horse farm, where you're likely to get sued for flying around a bunch right by them? Are you near, schools, hospitals, things like that, where you may be, less prone to want to use an aerial application method? So those are some other things to consider. Other typical considerations would be, are you on good ground? Can you operate on the ground, or are you going to rut up the site? Is it too wet? So on and so forth. Typical things we'd think about with any sort of question of operability on the ground. Another thing to consider when applying herbicides is the environmental considerations. Again, drift isn't as huge a deal. You obviously still don't want to be applying fertilizers off your own property. What we found from the research, basically anytime they've applied fertilizer near an SMZ, basically any amount of SMZ will do. I mean, even where they've cut SMZs down to 25 feet, you see a very temporary pulse in elevated phosphorus or nitrogen in a stream. It's just right after the fertilizer application. It goes right back to baseline, and very little of it makes it into the stream. So basically any SMZ will do. Obviously you don't want to apply fertilizer right to the SMZ, but consider forestry compared to agriculture, where with forestry we're generally using lower fertilizer rates, and then on top of that, even the most intensive land managers may be applying fertilizer, say, 4 times in rotation versus on an annual basis in agriculture. So we have a lot of issues, with the dead zone in the Gulf of Mexico and eutrophication in streams from too much nutrients in the stream. Forestry really isn't the source of that. We find that we do very, very well with our fertilizer application, and it's not really moving off-site. There is some evidence on sandy soils, such as the Sea Tree site we focused on in the last webinar, where it's a deep sandy soil down about 10 feet, very deep sand, and they've applied a lot of fertilizer on that site, and they can't quite account for all the nitrogen. And one theory is on some of these sandy soils, we may be leaching some of it out the bottom of the soil profile. But again, that's a relatively small percentage of our sites. And even there, if you've got a deep sandy soil, you've got deep-rooted trees. And so they're probably getting the vast majority of the nitrogen that's put out. So nutrients moving off-site doesn't tend to be much of a concern with forestry. As with anything we do, you're probably working with a contractor to do this, and you want to check that contractor. So here you see an example. Obviously, there's no trees around there other than this one right here, but that's an agricultural example of application with this truck. But you can see what they're doing. It's a very similar spreader to what we just looked at on a skidder, and they've got these tubs out per manufacturer recommendations. They run it for a minute, and they see, they weigh how much they caught in each tub and get a sense of whether their equipment is appropriately calibrated. Very analogous to what you would do with a boom sprayer for an herbicide. If you're applying aerially, obviously the applicator on the plane or helicopter needs to be calibrated appropriately, but on top of that, what industry commonly does is they go out and they collect catch data. And so they'll put tubs just like this. They would put 20 out in a stand, randomly distributed throughout the stand. The contractor flies over, applies herbicides, they go collect them, they bag all that fertilizer, and they may send it off to a lab, but all you would need is some sort of balance. You can weigh it, the area of each tub, and so you figure out the pounds of fertilizer mix that got applied per unit area, scale that up to a per acre basis, and you can get a pretty good estimate of what the variability is, from that application. And it's forestry, it's going to be variable, but also how close that contractor is coming to your target rate. And of course, if you start doing a lot of this, you can build some of that into the contract itself. And so again, sorry, this review slide copied incorrectly, but in general, most fertilizer is applied aerially. Some of it is applied by ground, by skidder, and of those aerial applications where we have relatively level terrain in the U.S. South, a lot of it is actually done by fixed-wing aircraft. So that's basically all 4 of our main points I wanted to hit on today. And so just to synthesize all this for you, on average, fertilizer does increase growth in southern pine stands. It absolutely, and we couldn't look at some of the data that's produced by some of these co-ops, but if you look at fertilizer growth responses across stands, it's a normal distribution. There's some stands that show tremendous growth responses, there's some stands that show no growth response, and there's a lot of stands right in the middle that show an average growth response, which tends to be about 25% for mid-rotation nitrogen application. So not all stands respond to fertilizer application. On average they do. We have a lot of variability. Different stands are limited by different nutrients, and often that depends on where you are. Again, those Pleistocene terraces on the lower coastal plain may be potassium loaded. Poorly drained clay sites on the lower coastal plain tend to be phosphorus limited. The vast majority of our sites tend to be nitrogen limited. We went over some of the tools, such as foliar nutrient analyses, soil analyses, and that CRIFF soil system that you can use to determine if your stand is nutrient limited and by what nutrients. And then again, fertilizer application certainly can yield economic returns, but it has its risks. And for forestry consultants and non-industrial private forest landowners, those risks are largely associated with a lack of tools out there for those constituencies, a lack of good data sets that you have access to that can show you, whether your stand is nutrient limited, and if it is, what the expected volume growth response will be. So hopefully in the coming years we'll see more of those tools become available. So thank you for attending the webinar today. Thank you to Sean and Eric and the folks at PINEMAP for putting this on, and I'd be happy to take any questions you may have.
While we're waiting on questions, I'm going to go ahead and post our web survey. So it might take just a second, but it should pop up very soon. And while that's loading, if you have any questions, just please type them in the chat box and we'll make sure Jeremy gets them. Well, if there aren't any questions, I'd like if everyone would just take a second to give our speaker a digital round of applause by putting your mouse over the smiley face under your name in the top left corner and selecting applause.
And if you have a question that you don't want to put into the chat box here, please feel free to email me. You see the name on the bottom left corner of the slide. Just Google my name and you'll find my website and can get my email address that way. But I can type it in here too. It's stovaljp@sfasu.edu. So please feel free to email me if you have any other questions. You can also call me, and my number is 936-468-2127. Okay, so we do have a question here. Niels is asking, does prescribed burning change potash or other nutrient needs? And you know, I'll take the cop-out answer you can do with almost any silvicultural question here and say it depends. So what we found is prescribed burning does alter nutrient cycling. And it in large part depends on the intensity and severity of the burn. So if you get a hot fire going through that burns a lot of your soil organic matter and sterilizes mineral soil, we can certainly see that volatilizing a lot of nitrogen, slowing down the cycle of other nutrients, and that would certainly make us stand more nutrient limited potentially and more likely to respond to nutrition. Potash, for those not familiar, is often made, it's often mined now, but historically it was made by burning organic matter and applying that ash to a crop field or a forest or whatever you were fertilizing. And so prescribed burning in general probably is going to, free up some of those nutrients like potassium that cycle very readily. It may slow down the cycling of phosphorus, again, which is a nutrient that cycles a little more slowly, so to speak, and its cycling is much more mediated by mycorrhiza, other biological activity. So that's sort of with a hot burn. What we found for a moderate burn, something that takes out some understory vegetation, doesn't do too much damage or put too much stress on your crop trees, that's probably actually going to accelerate nutrient cycling. It's not going to be hot enough to volatilize a lot of nitrogen. It basically, freed up the nutrients that were captured in your beautyberry or yopon or whatever your, understory vegetation might have been, and made them more plant available, at least for a short time. So in general, a moderate prescribed burn, something you would do as a prescribed burn, is going to be good for nutrient cycling. If it gets too hot, it may not be good for nutrient cycling. Where we've seen that affect nutrient cycling, you don't see as much in the literature on that combination of prescribed burning and fertilizer application. What you do see is more on prescribed burning and competition control. And so I know there have been those tandem uses of herbicides with fire, where you might apply the herbicide to get a good brown up so your fire carries well, or conversely, you do the prescribed fire to knock your vegetation back, stress it, it sprouts after that, and you can finish off the root systems with herbicide. And again, that's going to do very much the same thing fertilizer application is going to do. You're going to be shifting nutrients and water from your non-crop vegetation to your crop vegetation. So hopefully that got to your question, Niels. So Niels has another question. How deep should we go for soil test samples? I would say it probably depends on the site, but really you want to test soil where the rooting is occurring. And so, you can dig a deeper hole, close, a few feet from a tree. And if you're hitting almost all the fine roots, which typically occurs in the first 6 or 8 inches, sample the first 6 to 8 inches. If you're on a sandy site and, you can dig a hole real easy and get real deep, you may want to go a little deeper, and maybe even, depending on your, financial constraints, send some samples in from the subsoil and some samples in from the surface soil. But if your stand is phosphorus limited or potassium limited or something like that, typically you're going to want to look at the first 4 to 6 inches. That's on most sites where the majority of your fine roots are going to be, and it's the fine roots that are going to mediate where those nutrients are uptaken by the stand. So.
Looks like we have at least one more person typing, maybe? Or maybe not.
Okay, so we have another question from Jim here. Can you comment on the use of leaf area index as an indicator of likely response to nitrogen? And so leaf area index, basically low leaf area index, does indicate that your stand is likely to respond to fertilizer application if you apply a fertilizer that has the nutrient that's limiting growth on your stand. So the question then is, is the leaf area index low because that stand is nitrogen limited and not phosphorus limited, or limited by some other nutrient. Nitrogen is our most common limiting nutrient. And so odds are if you have a low LAI and you apply nitrogen, you should get a decent growth response that would make that fertilizer application economically viable under most circumstances. But if you're on one of these clay, poorly drained, lower coastal plain soils, that could be a phosphorus limited site. You could apply in and get no growth response. So again, even if you've got that leaf area index information, you really need more information to figure out what nutrient is limiting. The foliar analyses could come in pretty helpful there, provided you analyze for enough nutrients that you could spot something like a boron deficiency if you think that's likely. And I believe that slide had the critical level for boron as well. So nitrogen, again, it's going to be the most likely thing that's limiting on average, but we all know every stand is different. You got to treat every stand for the conditions on that stand. So.
Well, just in the interest of time, this room will be closing in a few minutes. If you have any other questions, I'm going to post both of our email addresses. You can either email Jeremy directly or pass it to me, and I'll make sure he gets it. And thank you, everybody, for attending today.